If your model looks great in training but breaks in production, odds are your pre-processing is inconsistent. We'll build an end-to-end scikit-learn pipeline, so the exact same transforms run at train and predict time. You probably see models that suddenly fail after deployment. Data distributions drift, or inference uses slightly different columns or scaling. By the end of this video, you will understand how to glue pre-processing and a model together, so the same steps run every time. That reduces surprises and makes debugging simpler. I'm Professor Pi, teaching AI foundations from basics to advanced, with simple, concepts-first Python that helps you solve bigger, real-world problems. Why this matters in practice. Teams iterate on features in notebooks, then copy ad hoc transforms into production code. That mismatch is the common failure mode. A proper pipeline makes success mean reproducible transforms and a predict call that behaves like the training loop. The cost is a bit more upfront, design and a discipline to keep feature definitions stable. At a high level, the idea is simple. Identify numeric and categorical columns. Fit scalars and encoders on training data. Save those fitted transformers and apply them unchanged at inference. This prevents subtle shifts and busted one-off handling of unseen categories. We'll build a tiny demo that proves the point. You will see fitting mistakes, construct a proper ColumnTransformer, wrap it with an estimator in a pipeline, and run safe inference on a new row. First, we'll illustrate the scaling problem with a small example. This snippet shows why fitting scalars separately on train and inference skews values. It fits a numeric scalar on the training set, computes the training mean and standard deviation, and then compares two workflows, transforming a new batch with the saved scalar versus refitting a scalar on that new batch. The refit approach makes the new data center on its own mean and produce different scaled values, which confuses the downstream model. The demonstration highlights how refitting on tiny inference batches amplifies differences, and why you should persist and reuse the original scalar rather than refit at predict time. Next, we'll create a tiny dataset and split it reliably. This example builds a small mixed-type dataset with numeric and categorical columns, and then splits it into train and test with a deterministic split. It uses a fixed seed, so the same rows always fall in train and test, which makes demonstrations reproducible. The tiny size keeps outputs readable and lets you inspect raw values before and after transforms. Using a deterministic split is important for debugging because it rules out randomness when you compare different pre-processing approaches. If you change the random seed, you will see differences in the fitted scalar and encoder parameters. Now we'll combine column-specific transforms into a single transformer object. This code bundles numeric scaling and categorical encoding into one ColumnTransformer that applies StandardScaler to numeric columns and OneHotEncoder to categorical columns. The point is to centralize rules so numeric features get centering and scaling while categories expand into indicator vectors. Parameters like OneHotEncoder handle unknown set to ignore, determine how unseen categories behave at predict time. Choosing sparse output versus dense affects memory and model compatibility. If you scale with a different method, like min-max, you would change just one place inside the ColumnTransformer without touching the rest of the pipeline. Next, we'll attach that transformer to an estimator, so pre-processing always runs the same way. This code creates a pipeline that first runs the ColumnTransformer and then trains a classifier. For example, LogisticRegression. The pipeline ensures that fit calls compute transformer parameters on train data, and that predict calls reuse those exact parameters. Hyperparameters on the estimator, such as regularization strength and LogisticRegression, change model capacity and accuracy, but do not affect the saved pre-processing behavior. Using a pipeline also makes it straightforward to serialize one object that contains both pre-processing and model state for deployment. Finally, we'll run inference on a single new row that includes an unseen category. This snippet demonstrates safe inference by passing a new row through the fitted pipeline, including a category value that did not appear in training. Because the OneHotEncoder was configured to ignore unknowns, the pipeline handles the unseen value without error, producing zeros for those missing indicator columns, while the scaler applies the original training statistics. This shows how the pipeline isolates inference from ad hoc refitting. If the unseen category matters a lot, you might choose alternative encoders or grouping strategies, but the pipeline prevents silent distribution shifts during prediction. Recap: what we built is an end-to-end scikit-learn pipeline that locks pre-processing and modeling into one repeatable object. Use this when you need reproducible predictions and simpler deployment. One caveat is that pipeline objects must be versioned and updated carefully when you change feature definitions, because changes break compatibility. Next step, tune the estimator regularization parameter and measure performance with cross-validation while keeping the same saved pipeline for inference. That gives you a controlled way to improve accuracy without risking inconsistency. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.